Okay, guys, can you guys hear me?
Yes.
Okay, perfect. So let's give it a few more minutes before we get started, okay? Today is actually the open course for our first lecture. We're actually waiting a little bit longer for receiving more attendance, okay? So maybe let's have it about more than 3 minutes. Okay, maybe 3 more minutes, and then we're gonna start our lecture at roughly 7:05. Okay, 3 more minutes while we're receiving more attendance. And also for your information, as this is like an open course, we're actually expecting a lot more students. So in order to make sure the quality of our lecture, please try to unmute yourself, okay? So by default, as long as you go to the lecture, you're gonna be put into mute, right? So make sure you can mute yourself. Normally speaking, our regular lectures, we have a lot of interactions. So as long as you got a question, you can always unmute yourself and ask me the question using your microphone. But this is like an open course. I think we'd better just put all your questions into the group chat. So as I'm always monitoring the group chat during the lecture, I think it's easier to just try to make sure the quality of our open course. And thanks for understanding. All right. And also another information is there might be some parents in the group, and today's lecture is going to be in English only. We're not speaking Chinese or French. All right? 那么今天的讲座呢，我们只说英文，我们不说中文和法语。OK? Des langues officielles aujourd'hui est l'anglais seulement. Pas l'anglais, pas français, pas chinois. OK? C'est bon? Yeah, just for your information. So we're gonna get started at 7:05. All right, I think it's 7:05, so let's get started. So first of all, welcome guys to our open course. Today is actually the first lecture for our Euclid bootcamp, so we will make it as open course. Try to give more opportunities for more students who are interested in our bootcamp. All right, so if everyone's there, so let's get started. Okay, so today's lecture, we're gonna focus on the Euclid, right? So I assume you guys already have some rough idea how the Euclid works. But for the guys who are not so familiar, I might take roughly 5 minutes to give you guys a quick overview about Euclid exam and try to answer some potential questions that students and parents, they like to ask me from time to time. All right, so let's jump to it. The first one is we're gonna spend some time talking about the Euclid exam. So in Chinese, we have a saying, 知己知彼,百战不殆, right? So in English, say you got to know your enemies. So for the Euclid exam, overall speaking, this is like an exam racing to from grade 9 all the way to grade 12. It's not really focused on the student from a specific degree. As long as you know like the Euclid better, you want to participate in the Euclid, you're more than welcome to join a Euclid. So first of all, we need to talk about how to understand the Euclid exam, how the Euclid works. Basically, you have 2.5 hours, 2.5 hours, and you're looking at 10 problems. And for each problem, it worth 10 marks. It's pretty even distributed without like to say this is a difficult problem, it worth more marks, or this is an easy problem, it's fairly cheap, but they're actually the same thing. And for each problem, normally speaking, it has like 3 parts, A, B, C, 3 parts. And there are actually 2 types of questions. As long as you see like a light bulb here, means this kind of question, you could just give a number. That's it. You don't have to show your work. All the detailed derivation process, not so necessary. But as long as you see there's like a handing sign, right, writing sign, it means you have to show your work. If only present a number, even though this is a correct number, you won't get too much mark. You need to show your very detailed process, how your derivation, how is the thinking process, which is very important for this type of problems. This is quite different from the AMC, right? AMC, even though it's Amy, you only need a number, right? But for Euclid, it is very important. You need to show your work. A very clear, a very well-organized presentation is going to be crucial in the Euclid exam. Okay? So second part, talking about all the 10 problems, where they are they the same complexity or they're kind of like a curve talking about complexity? And the answer is actually the complexity varies for these 10 problems. For the first 4 problems, we see these are pretty much the easy peasy problems. You have to do them and you have to do them right. As long as you lose some mark for the question number 1 to question number 4, you won't be so competitive for the entire Euclid exam. So you have to make sure the first 4 problems, you must take them out. And then from question number 5 to question number 8, these are actually considered to be the critical questions or like the critical problems. So if you want to do a very good job in this Euclid, you want to have your certificate, it is very important you do a good job for question number 5 and all the way to question number 8, because they are pretty much the essential part. All right. And then the last 2 problems are fairly difficult, especially question number 10. So you know what, actually later I'm going to show you a strategy. In order to have a good mark in the Euclid exam, you don't really have to take all those 10 problems evenly. You really have to pick a little bit kind of like strategy, focus on some easy and critical problems, and then try to more strategic for question number 9 and question number 10. All right. And then the second part is how much you need to get in order to get kind of like a good score in the Euclid exam. So normally speaking, Euclid actually give you 2 types of certificates. The first one is pretty much everyone knows that is 25%. Also, we call it like the cutoff score. So every student, as long as you're scoring in the top 25% of all the competitors, you will be receiving a certificate of distinction. So this is, I think, quite understandable. And the second part is the 5%. That one is actually very important. As long as you go to the 5%, it means that, okay, you really did a very good job. And if you want to use the Euclid as kind of like information for your college application, this is going to be very helpful. All right, so these are the 2 types of certificates. And then the Euclid is always bound with a scholarship. So the thing is that actually a lot of students go to the Euclid exam, and most of them are actually focused on two grades. I'll say most of them. One is actually grade 11. The other one is grade 12. Okay, these are, I would say, the major population the student goes to the Euclid exam. And there are actually different kind of like use for this like two groups of students. As long as you're in the grade 11, Euclid is going to be very helpful for a college application. Okay, so if you want to go to Waterloo, if you want to go to some other like Ontario or Quebec universities, if you can show a very good score from the Euclid, it's going to be very helpful. So therefore, trying to have your Euclid before grade 11 is something very important. But what if you are already grade 12? Do you still need to go to the Euclid or still like valuable? The answer is still yes, because as long as you're grade 12, Euclid can help you to get your entrance scholarship from most of the universities, especially for the Waterloo, right? The Waterloo is actually hold the Euclid exam. So this is actually what I got from the website. So admissions and scholarship. In order to be eligible for the entrance scholarship in the Faculty of Mathematics, you need to get either Euclid or the CSMC. Actually, the reality is people put more emphasis on the Euclid rather than the CSMC. So therefore, having a good score for the Euclid is actually very helpful for your college application and also good for the scholarship application as well. Okay. So that being said, having a score, having a certificate is very important. Top 25%, you're going to have one score, like one kind of certificate. The other is like 5%. So normally speaking, what is the score for me to get a certificate? I think for the 25% is fairly straightforward. We also call it the cutoff score. Means if you're lesser than 25%, you won't be able to have a certificate. Where to get it? You can actually get it from the official website. This is actually a statistic I got from Euclid 2019, because in 2020, we didn't really have the Euclid due to the pandemic situation, right? So I got the latest and greatest information from the year 2019. You can see the cutoff score is actually 68. As long as you're more than 68, you'll be able to get the 25% certificate of distinction. Okay, that is fairly straightforward. Then what about the 5%? This is actually a very mysterious part because people keep asking me, sometimes they told me this is like 80, sometimes like 90, sometimes it's even like 95. So people always get confused. What is the 25? What is the 5%? Okay. So in order to answer this question, you know what? Euclid is not as user-friendly as AMC. Every year after the AMC is going to have a statistics, right? Really giving you all those kind of like breakdowns for each score, how many students you have, what is top 1%, top 10%, so on and so forth. But what about the Euclid? Euclid never directly give you the answer, but you have to do a little bit investigation and analysis to figure out the answer by yourself. So what is the top 5%? You can actually do such a quick analysis. I give an example from the year 2019. This is actually a results from the Euclid exam. You can find out, okay, in total, you have 20,944 students participate for this exam. So if you want to take 5%, you are roughly looking at 1,047. So as long as you're lesser or you're greater than 1,047 students, means you are the top 5%. If you check for all those distributions, you'll find out, see, roughly here, right? 81. So actually that is the case. In the year 2019, 81 is the percentage you'll be able, always to say, is the cutoff line, and you will be able to get your top 5% certificate. Okay? And I actually do the same thing again for the year, okay, 2018. 2018 is exactly the same thing. You have 18,401 students. The same thing, you want to do a 5% calculation. That one is going to give you roughly 920. So 920 should be something around here. You see, 76. So that being said, if we use the history to tell the future, roughly in order to get the 5%, the top 5%, you are roughly looking at from 76, 78, all the way to 80, 81. So that's pretty much a rough estimation to give you guys a little bit idea. Okay? So with that information in place, I think most of the student is going to be asking me a very intuitive question. Okay, you're telling me roughly 80 is going to be a big score, like a good score, right? And how can you get 80, right? How can I get 80? 80 is a good enough score. And is there any kind of strategy to get 80? The answer is yes. So let's check it out. Like I said, normally speaking, the first 4 problems, the no-brainer, you have to do them, you have to do them right, right? And then all the way come here. What about question number 5 all the way to question number 8? So these are actually what I call the critical problems. And that is actually the gravity, that's like the focus of our lecture as well. So you have to minimize all those unnecessary mistakes, unnecessary errors for this number 8, number 7, number 6, number 5 problems. All right? And also talking about your time, your like Euclid actually contains 2 hours and a half. I wish you guys can put 2 hours for the first 8 problems. 2 hours. In the reality, you can actually put 1 hour, 45 minutes to do real calculation, the order presentation, and then maybe put another 15 minutes as a validation. You can check your work. Okay, because the first 8 problems, they're not so crazy. You should be able to do them in roughly 2 hours and 1 hour, 45 minutes. And then for the remaining question number 9, question number 10, you don't really have to do them all correct. You have to be a little bit selective. What I suggest for my students is roughly you have to do question number 9, A part, and at least part of the B part. Because all those problems, they're not directly jump to the super difficult questions, they're progressively. Even though number 9 is a little bit difficult, but A part and part of the B part, they are actually doable. And the same thing applies for the question number 10, only focus on the A part. You don't really have to spend too much time on the B part and C part, only focus on the A part. If that's the case, let's do a quick calculation to see how much scores you can actually get. Like I said, the first 4 problems, you have to take full mark, no brainer. And then from number 5 all the way to number 8, you can have some tiny errors, but you can't afford to have too much. So I would say roughly you're going to have these 2 parts. You can have roughly 78, roughly to 80. Okay, 80 would be fantastic. You do them all correct. But you can actually suffer 1 or 2 marks lose. That's not a big problem. You're looking at roughly 78 to 80. And then if you can do question 9, A part, and part of the B part, at least you're looking at 3 marks to 5 marks. And for question 10, A part, you can actually looking for at least 2 marks to 3 marks. So that being said, if you do a quick calculation, you add all them together, you actually roughly get maybe 83 to 88. Okay, trust me, if you get 83 to 88, no matter what, you're gonna have your certificate, top 5%. Okay, so this is like an overall strategy. Okay, you have 5 hours and a half, spend the first 2 hours in the first 8 problems and maybe 30 minutes for the last 2 problems, and then try to kind of like leverage your effort, your kind of focus. Do not evenly do it. Do not do an even distribution. Really focus on the very important part. All right, that's pretty much a big direction. And then talking about our 10 lectures. So how we organize our 10 lectures. Our 10 lectures are actually organized by different chapters. And these are actually based on the analysis for all the past Euclid exams. Our first lecture is actually today's lecture. We're going to focus on the 2D geometry, pretty much for the triangles and also the quadrilateral related discussions. Because this part actually takes roughly 25% of all the problems that has been tested in the entire Euclid history. I have already did analysis. I count all the problems one by one, and this is actually the number. And then next lecture, we're going to focus on the circle and the 3D geometry. That one will take roughly 88% of all the problems that tested before. And then for the third lecture, we're going to move to the coordinate geometry. Okay, all the way from here, we're going to stop here for a sec. Check it out. If we do a calculation for the first 3 lectures, we already take roughly 45% tested by the entire Euclid. So that being said means what? Means Euclid actually put a huge emphasis for the geometry part, 2D, 3D, and coordinate. So if you can have a very good understanding for the geometry, that's going to be very helpful for the overall Euclid exam. All right. And then moving forward, we're going to go to the exponents and the logarithm. This is pretty much every year you're going to have one problem. That's for sure. You're going to never have any problems. Every single year, one problem for the exponents and logarithm. And then we're going to go to the advanced functions and the polynomial. That one will take roughly 15% for the entire Euclid. And then we're going to go to the trigonometry, 8%, the sequence problems, roughly 10%, counting and probability, 12%, and the number theory, which is actually 8%. If you do a quick calculation here, you're going to find out adding them together is slightly more than 100%. And the reason is because sometimes a problem, there's kind of like a interdisciplinary problem, like a problem that tests you both a trigonometry and also some sequence related problem. So it's kind of like an overlap, right? But generally speaking, I think like the Euclid exam have a very good distribution. All the chapters, they're kind of very segregated. They can put emphasis in one part and then another emphasis on the other part. All right. And then in the last lecture, we're going to give you guys a mock exam. We're going to pretty much use all the technology we introduced for our entire lecture and give you guys some real problems. Hope you guys can do a just kind of mocking. All right. So the most important thing for our lecture is not really giving you guys all the problems one by one. I think you can get to it by yourself. Well, the most important thing for our lecture is to teach you guys the strategy. Fish and fishing. Which one is more important? You have the answer. So basically speaking, each lecture is organized in such a way, we're going to break it into two parts. Okay. The first part, we're going to take maybe roughly 20 minutes, 15 minutes to talking about the concepts, the most important concepts that you have to know in the specific chapter, like all the rules, all the theorems, all the formulas, so on and so forth. We won't be able to give you super detailed stuff due to our kind of time limitation, but try to give you guys a big idea, right? This is kind of the Booleans, boom, boom, boom. You have to remember and in order to go for the Euclid. The second thing is I want to give you guys the most typical problems, the most important typical problems. You know, Euclid is the same people, like at least the similar people doing the kind of the exam year by year. So people actually having kind of a momentum, right? You always love what you love and always hate what you hate. The same thing applies for everyone. So we'll see the order of the Euclid exam actually is very consistent. They like to test something year by year. So after understanding all those problems, all those Euclid problems, we have already select out the most typical, the highly tested problem year by year. And then I'd like to give you guys a kind of big direction. What are the categories are, and what is your common strategy, common approaches for all those problems. All right, so this is actually the two important parts for our lecture. And of course, after each lecture, I'm going to give you some problems. Most of the problem come from the Euclid. I want to use the real problem just to utilize the technologies we introduced during the lecture. I hope you guys can apply them, learn something and apply something. This is a more effective learning process and a learning pattern as well. All right, I think that's hopefully it's a short and brief introduction about our first part. If we're all good, let's jump to our first lecture. All right, the first lecture, we're going to talk about the 2D geometry. Pretty much, like I said, focus on the triangles and the quadrilaterals. Okay, first thing first, let's go to some concepts. Very important concepts that you have to know for the 2D geometry part in the Euclid. So most of them, I think, they're super straightforward. You guys can actually follow me to do a quick recap. The first one is the super straightforward Pythagorean theorem. You learned that from the kindergarten, I gotta say. If you have a right triangle, a squared plus b squared equals to c squared. Don't really look down this like a tiny thing. Actually, Euclid likes to test it from year to year. Even though for question number 9, for one of our sample questions today, you're gonna see you have to use the Pythagorean theorem. The second one, you're going to really understand how to determine the congruency and similarity. The congruency and similarity, I understand this kind of the foundation for the entire 2D geometry. Most of the complicated and flowery problems are actually elaborated from the congruent triangles and the similar triangles. So for the congruency, you need to understand how to determine two triangles that are congruent. So you have the SSI, size, side, 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 right? Angle, side, 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 angle, side, right? These are the basic things in order to understand how to determine two triangles that are congruent to each other. And especially if you have a right triangle, you can actually use the HL. H stands for the hypotenuse, L stands for the one of the leg, right? They don't have to have three conditions. So generally speaking, in order to determine two triangles that are congruent to each other, at least you need to have a side condition, right? At least you need to have a side condition. If you only have the angle condition, you won't be able to determine two triangles that are congruent to each other. These are very basic information. Then what about similarity? In order to determine two triangles that are similar to each other, you can have the angle, you can have side, 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 three sides that are proportional to each other. You can have the angle, side, side. You can have the HL, right? These are also very common strategies you actually utilize from time to time in order to determine two triangles that are similar to each other. Actually, a quick trick. This is actually, I want to give you guys is, according to the analysis for the entire Euclid exam, you can find out this guy is barely tested. So most of the time when Euclid wanted to determine two triangles that are similar to each other, most of the time, based on the analysis, they focus on the two angles or two sides plus an angle. This is only based on the statistics. There's no reason. It's only kind of a preference of the author from the Euclid exam. All right. The third thing is where you can find similar triangles. Okay, is there any common type for the similar triangles? In our AMC lectures, we actually give you about like 12 different types, right? It's very complicated, but for Euclid, it's way more easier than AMC. They don't really test you something so flowery. Generally speaking, they only test you two typical patterns. One is here, what we call the sand glass timer shape. As long as the two triangles are actually head to head, right? They're flipped. These two triangles, they might be similar to each other. Or the other one is actually the pyramid shape. Okay, so this little triangle and big triangle, they're actually similar to each other. Trust me, from Euclid's perspective, this is good enough. You don't have to waste your time to a lot of flowery things. The other 10 types we talk about for the AMC, not really applicable for you, for like Euclid all the time. And then there's actually one more thing which is super important for the AMC and also for the Euclid. This is the first cosine law. The first cosine law. Why I put it here? Because the first cosine law is actually proved by using the similarity. And you can find actually three triangles that are similar to each other using the first cosine law, right? So let's say this is A, this is B, C, D, E. You're going to have A squared equals to B times B plus D, right? E squared plus D times D plus B. And C squared equals to B times D. Right? This is like a very intrinsic form of the first cosine law. And Euclid actually tested this from time to time. All right? So as an example, later you can see that in the 2010 Euclid question 6b, they're just directly using this first cosine law. If you know the first cosine law, you don't have to waste your time doing the similarity related calculations. You can actually use one single formula and save your time significantly. All right? And another thing here I want to talk about is in the similar triangle, there's actually a very important property. This property, I think, is very conspicuous for everyone, but bear in mind, this property will be tested from time to time, from year to year. This is actually something like this. If two triangles, they're similar to each other, so the areas ratio, this is area prime, will be actually equals to the side ratios perfect square. Is that right? The area ratio will be the similarity ratios perfect square. This is actually something very important, and Euclid actually tested from year to year. And this is actually not only works for the triangles, it also works for any kind of shapes, right? Or the quadrilateral or like the polygons, so on and so forth. As long as you see two shapes that are similar to each other, then automatically you can see that the area ratio will be side ratios perfect square. And if we can elaborate a little bit, the same thing, the volume ratio will also be the side ratios perfect cube, right? This is actually something very important for Euclid as well. All right, so let's continue. What about the other very important concepts you need to know? Number 4, you're actually talking about something, like the isosceles triangles, right? This trapezoid, these kind of basic shapes, you need to understand them, and they're going to be tested from time to time, okay? And then number 5, we're going to talk about the area method. Oh, trust me, area method is like so important. Actually, if you go to the Euclid exam, you do a quick statistics, you're going to find actually roughly 45% of the entire geometry, 45% of the entire geometry problems, they're actually talking about the area method. This is something so important. So what kind of things you need to remember? There's some basic stuff you got to remember. Let's say if you have a triangle, this is H, this is A, right? So the area will be what? This is the basic one, H times A divided by 2, right? And also, what else you can have? If this is B, this is C, this is theta, you're gonna have 1/2 AB sine theta, right? This is also something super important. What else? You can actually let P equals to A plus B plus C divided by 2, and S can be equals to P minus A, P minus B, P minus C, right? This is the famous Heron's formula, right? I think these are something quite understandable. You should pretty much bear in mind for all those basic concepts, right? And also, what about when you have A, B, C? This is an equilateral triangle. As long as you have an equilateral triangle with the side length equals to A, you should have a conditional react. The height of the equilateral triangle is going to be under 3/2A, right? Under 3/2A. And the area of this triangle will be what? Under 3/4A square. These are the basic things you need to remember. Pretty much bear in mind, right? Without any doubt. Okay, this is actually number 5. Number 6 is the famous Sine Law and the Cosine Law. These two parts are also very important, and the AMC and Euclid, they both test them from year to year, right? For Sine Law, what you have here, A, B, C, A, B, C, you're gonna have A over sine A equals to B over sine B equals to C over sine C equals to what? 2R, right? And what does this R stands for? This R stands for what? The radius of the circumcircle, right? The radius of the circumcircle. All right, this is the famous sine law. Then what about the cosine law? The cosine law is also very important, if not even more important. A, B, C, A, B, C, then cosine A equals to what? C squared, B squared minus A squared, 2BC, right? These are actually something very important that you have to know. Okay? I think these are very basic concepts. We're not talking about something too like techy, right? You should understand it very quick. And then what about number 7 is the famous angle bisector theorem. That is also very important. You have to know them because these are like the foundation. This is actually the foundation for most of the problems. As long as you see an angle bisector, these days, your first reaction shouldn't be, okay, these two angles are the same. Oh, these, of course, angle bisector is going to break the same angle into two equal parts. But these are so easy peasy stuff. While on the contrary, your first reaction should always be AB over AC equals to BD over DC, right? This is actually the angle bisector theorem that you have to know for the Euclid. Okay, the first 7 theorems I have to say these are easy peasy theorem, and you have to know them. You have to know them right. Okay, and then there are still some theorems that are not so important for Euclid. AKA, they're not tested every single year, but I think it is quite important for you guys to remember this. So let's say number 8. So we'll say I'll make a dash line here. This is not so important, but still important theorems. Okay, number 8 is actually the Stewart theorem. Okay, if you go to AMC, this is a must. But Euclid is kind of like, okay, you don't really have to know it so well. But if you know it, it's really going to help you a lot during the calculation process. If you have a triangle ABC, right, you have the 3 sizes, C, B, and this is A, right? And then you have any kind of a line, AD actually just cuts the triangle into 2 parts. So D is kind of a dynamic point. So this is D, this is M, this is N, right? Then automatically there's a relationship between these 7 different segments. So what's the relationship? It's M, A, N, M times A times N plus D times A plus D, and equals to B times M times B plus C times N times C. Okay, this is the relationship. And in order to make it easier, because this is like a long and a nasty relationship, right? Then what you can do, you can actually do something quick. You can actually try to remember this formula into a sentence. A man and his dad put a bomb in the sink. A man and his dad put a bomb in the sink. This is like a shortcut way for you guys to remember the Stewart theorem. All right, then let's go to number 9. Another important thing, very important, but not necessarily tested every single year in Euclid, is the famous Menelaus. Menelaus theorem. In AMC, it's for sure, you have to know, but Euclid is kind of okay, but it is strongly recommended. You need to remember this. So that's going to be, as long as you have a triangle ABC and you have a transversal line cut, the triangle ABC. So nothing is really special. C prime, B prime, A prime, they're just like random points. As long as they collinear, right? You can have such a relationship. BA prime, A prime C, CB prime, B prime A, AC prime, C prime B equals to 1. All right, so this is actually the famous Menelaus. So basically, you can find out, see, from here to this point, going back. And then from this vertex, go to another point, then going back. From this vertex, going to another intersection point, and then going back. This is kind of like a closed loop. You'll be able to traverse the entire 3 vertices in the triangle and construct such a relationship. All right. And the last one you need to know is the Siva. The Siva theorem says what? Whenever you have a triangle, you find any point. Again, this is a dynamic point. And then you do a connection, right? And then try to do an extension and intersect with the 3 sizes. you're going to have A, B, C, A prime, B prime, C prime. Then automatically you have such a relationship, AC prime, BC prime, BA prime, A prime C, CB prime, B prime A equals to A, equals to 1, right? So this actually, let's do a quick comparison between this Menelaus and Siva. You can find out these two theorems actually reveals an intrinsic property of the triangles, right? There's nothing too flowery. All the points are actually giving at random points, right? They're all dynamic points. However, you can find out, oh, there are some intrinsic relationship within the triangle, even though the 3 points are actually giving quite random, right? But this kind of relationship given by Menelaus and Siva, they're very stable. You don't really have to do a lot of tweak, and you get this relationship all the time. All right, I think that's pretty much what I want to say, talking about all those very important concepts for this Euclid. All right, so far so good. With all the concepts, let's go to some real problems, right? We'll see how to use the concepts we introduced and to solve the real problems in the exam. So the second part, we're going to go to problems. So in the problems, we like to give you guys some typical problems. The problem will be tested from time to time for the Euclid exam. And generally speaking, I think there are two major types talking about the triangles and the quadrilaterals. The first big part is actually the area problems. Like I said, more than 45% of the Euclid problems, they're actually somehow testing the area. So we need to have a very good understanding about how to deal with the area problems. So if you can have a quick recall about what we introduced previously, like I said, area method, you're basically using different kind of area formulas and you'll be able to solve it out, right? However, there's one type, like I mentioned previously, is kind of tangled with the similarities. As long as in the Euclid, if you're dealing with kind of like similar triangles, similar shapes, and also the question asks you to determine some area method, you know what? 95%, I can't say 100, but 95%, you're trying to use what? The areas ratio is actually the similarity ratio's perfect square. Okay, the area ratio is the similarity ratio's perfect square. So trust me, this is actually a very important big direction. Okay, so let's try to give you some problems. Try to see how you're going to deal with such a problem regarding the similarities and regarding the area ratio and similarities ratio. Okay, so let's get started. The first problem we're looking at is a problem that comes from, okay, drag it here. The first problem we're looking at is a problem that comes from 2007 Euclid, question number 8, B part. Okay, so let's have a look how we're going to do such a problem. So the problem says in the diagram, the area of the triangle ABC is equal to 1. There's a trapezoid DEFG is actually constructed such that G is on the left of F, DE is parallel to BC. Of course, the trapezoid, you're going to have the top and bottom parallel to each other. And EF is parallel to AB, and DG is parallel to AC. Ah, that makes sense. Means your trapezoid, the 1, 2, 3, 4, 4 sides, they're all basically parallel to the 3 sizes of the triangles, right? And then the question is asking you to determine what is the maximum possible area of the triangle DEFG. So basically, you're dealing what is the area for this trapezoid DEFG. Okay, first thing first. Number one, I want to tell you like a golden rule. These are all the conditional react. As long as in the Euclid exam, the question asks you to determine any kind of polygon's area of a polygon. You see, trapezoid is also a polygon, right? Okay, As long as the question asks you to determine the area of a polygon, your first reaction is never calculate directly the polygon's area. However, you're going to do a little bit conversion. Convert from a polygon's area into triangle's area. This is super important. Euclid will never directly ask you to determine the area of a polygon, the real solution. Always you're going to do a little bit conversion. Convert a polygon's calculation into a triangle's calculation or many triangles calculation. This is actually something very important. Okay? And to give you a little bit of explanation, why? Because we don't have so many technologies to determine the polygon's area, right? Even though this is a trapezoid, you think it's better, but you don't really know. You see, in order to do this, I'm gonna know what is the bottom, what is the height, what is the top, and what is the height, right? There are like so many things flying there. I really have no idea what to do. However, if I do a conversion from this polygon into a triangle problem, I think my life can be a lot more straightforward because I have so many technologies to determine the area of a triangle. So let's check it out. How are we going to do from a triangle's perspective? Okay, now our big direction is trying to solve the problem from a triangle's perspective. Okay, triangle. And we have a bunch of, see, this is parallel, this is parallel, this is parallel, then automatically we're actually generating a bunch of similar triangles, right? This is actually what? This is our pyramid shape we just talked about previously, right? Pyramid shape. Okay, as long as you see similarity, you see the area, your first reaction is maybe you're going to find out the relationship. The areas ratio is the similarities ratio's perfect square. So in that case, let's check it out. How are we going to deal with such a problem? You know what? To make my life a little bit easier, what I can do is I can actually let BG over BC equals to BD over AB equals K. Why? Because a similar triangle, you're going to have a similarity, right? If you have no similarity, there's no way for you to play with your similar triangles. This is like the basic concepts, right? Okay, if that's the case, let's check it out. So try to make my life easier. I know the area of this triangle ABC is equal to 1. Okay, then what about I give the three sizes? This is A, maybe this is C, and this is B, okay? Now I actually give you what? A kind of a proportional relationship. So that being said means what? BG over BC equals to K. If this is A, this is going to be KA, right? And this part is going to be what? 1 minus KA, right? Same thing. If this is KA, this is going to be KB, right? So this part is going to be what? 1 minus KC, right? So this is C, right? And then you see, because the three sizes, they're actually parallel to each other. So it's very easy for you to say this is going to be what? 1 minus KB. This is going to be KB, right? I think this is quite understandable. Nothing really flowery. Okay, as long as you have this, I think your idea can be a little bit clear. If you want to determine the area, let me change a different color. For this trapezoid in the middle, what you can do, you can use the total area of the big triangle ABC to subtract the three small triangles, BC, BGD, ADE, ECF, right? The three little ones in the middle, all right? And then so let's check it out. How can we determine the area of the three little triangles? Check the first one. Let's go and check the first one. The first one here, this triangle is actually similar to the entire triangle ABC, right? Triangle BDG is actually similar to triangle ABC. According to our schedule, if the similarity is the K, so the area ratio is going to be similarities ratio's perfect square. So my area is equal to 1. This is actually given by the question, right? The total area of triangle ABC is equal to 1. And BDG triangle, the similarity for this guy for the entire triangle ABC is actually K, right? So therefore, its area is going to be k squared, right? Same thing. Triangle EFC is also similar to triangle ABC. Let me change a different color. EFC, this triangle, is also similar to the big triangle. So the similarities ratio, perfect square, is going to be the area ratio. So what is the similarity ratio? Of course, K, right? K is the similarity ratio because you see here, this is KB. Then I take a perfect square. This is going to be what? This is going to be the area of triangle EFC. And then you just basically have to do the same thing for the last one, ADE. ADE triangle is similar to triangle. Triangle ADE is similar to triangle ABC. So this is 1. So what is the similarity ratio? 1 minus k. So this is going to be 1 minus k perfect square. So with all those information, the area of the trapezoid is going to be 1 minus k square minus k square minus 1 minus k perfect square, right? The total area of this big triangle ABC minus the blue one, the green one, and also the red one, right? So this is going to be your expression, 2k minus 3k squared. This is the total area of the trapezoid, okay? The trapezoid. And question is asking you, okay, what is the maximum? What is the maximum or minimum? Let's check it out. Yeah, what is the maximum value of this guy? So as long as you see this actually goes to a very, very important concepts for AMC and also for the Euclid is as long as you have a quadrilateral, right? You have like, as long as you have this quadratic equation, how can you determine the maximum and the minimum value? I think this is something super important and you need to know that. Okay, how to determine the maximum or minimum value of a given kind of like quadratic equation, right? The most important thing is you need to know the domain. So, okay, where does K comes from? What is the range for K? So let's check it out. Let's check it out. At the very beginning, I do what? I actually make such assumption. BG over BC equals to BD over AB equals to K. So that being said, my K can't be too big. My K must be between 0 and 1, right? Because BG is actually a segment for the entire BC, right? So BG cannot be more than BC. So the K must be between 0 and 1. So you're actually looking for 2k minus 3k squared. As long as k is between 0 and 1, what is the maximum value? I think that one is fairly understandable, right? You need to actually use the graph, right? The graph goes like here, and you're looking at basically this is 1 over 3 as the symmetric axis, right? And you're looking what from 0 all the way to 1. So the maximum value is, of course, whenever k equals to 1 over 3. So 1 maximum is actually when k is equal to 1 over 3. You plug in the value, they give you 1 over 3. So the correct answer for this problem is actually 1 over 3. That's it. You see, it's actually fairly straightforward, right? As long as you figure out, okay, you are dealing with the area of trapezoid. That's not good. Convert it into triangles. As long as you see the area of triangles, plus you have this similarity thing, your first reaction is always similarities ratio. I make a perfect square. That's going to give me the area ratio, right? And moving forward, I basically use like the quadratic equation from the different domain. I'll try to determine the maximum and minimum is good to go. All right, so this is actually our first problem. Fairly straightforward problem, and you get what you need. If all good, let's go for a second problem. We're going to use exactly the same strategy to solve another problem. So the second problem we're looking at is actually a problem that also comes from Euclid. So it's here. This is a problem that comes from 2001 Euclid. Question number 9. Okay, question number 9 considered to be relatively difficult, but still same strategy. Let's check it out. So the question says you have a triangle ABC is a right angle at B and has the side lengths which are integers. Okay, which are integers. Here, I'm going to give you a very important quick note. Conditional react or golden rule. This is our golden rule number 2. As long as you see some integers, some side are integers, some variables are integers, most likely, I'm not going to say 100%, but most likely you're going to use some basic number theory related discussion. Number theory related discussion, aka from Euclid's perspective, you're going to do some factorization. Okay, this is kind of a golden rule. As long as you see something as an integer, most likely you're going to use some factorization during the calculation process. So let's check it out. So you have basically like 3 sides that are integers. A second triangle PQR is located inside the triangle ABC as shown, such that the 3 sides that parallel to the ABC. You see, the 3 sides that parallel. So AKA, these 2 triangles should be similar to each other, right? This is actually a conditional react. And also the question says, the distance between the parallel line is 2. That means, okay, here, 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 they're all like 2 away from the big triangle. Okay, with all those information together, the question says, please determine the side lengths of all possible triangles ABC such that the area of triangle ABC is 9 times of that in triangle PQR. Triangle ABC's area is 9 times of triangle PQR's area. I think this question actually gives you a lot of hint. All the way comes to here, you should already get some ideas. The question gives you 3 parallel lines, then automatically you understand triangle ABC is actually similar to triangle PQR, right? This is no-brainer. And also, on top of that, the question says what? The 2 triangles area ratio is 9. 9 is what? 9 is a perfect square number. Then automatically, you should actually use our golden rule number 1, right? So you want to say, okay, triangle ABC and the triangle PQR, their similarities ratio is actually 3:1, right? I think this is quite understandable, 3:1. And then most likely you're going to do your following work just based on the relationship between this 3 and 1, these 2 sides, and taking from there, you'll be able to get what you need. All right, so let's check it out. How are we going to do this? Okay, you have 2 triangles. You have the similarities 3:1. I think the most straightforward ways, you're going to list out the size, right? And then find out the 3:1 relationship of the size. And then taking from there, hopefully you can get an answer solved. So that being said, this is actually very intuitive, right? So what you're going to do is you can actually maybe here, I'm going to do some, I'll say this is my side B. AC is actually my side B. AB is my side C, and BC is my side A. Okay? According to our analysis, we just figure out the similarities ratio should be 1/3. So here it's going to be what? 3/B, right? PR is 3/B. I'm going to zoom it a little bit. QR is going to be what? 3/A. And PQ is going to be what? 3/C. Okay, that's it. All right. Taking from there, I have like ABC, 3 things flying there. And I have 3/A, 3/B, 3/C is there. But I cannot do too much based on this. Most of these calculations, I need to construct a kind of like a relationship, right? With this relationship, I will be able to maybe plug in the value, manipulate something and take it from there. A relationship is nothing but what? But an equation. I need to have an equation here, right? Okay, how can I construct an equation? I have to go go back to check. It looks like the only condition given by the question is what? The kind of, let me check. The only condition given by the question is kind of like what? It's kind of like this relationship is like 9 to 1. That's it. No more than that. So that being said, maybe I need to use the small triangles area and big triangles area, do some construction, figure out some relationship, right? So I think the most straightforward way is let's try to do a little bit connection here. Here, here. So that being said, you can actually break the big triangle into actually 4 parts. You see, you have 3 trapezoid, right? And you have you see the 3 trapezoid I highlighted using this different color, right? And also the little triangle in the middle. So my total area is going to be the sum of the 4 parts. Okay, so let's try to find out the relationship from here. My total triangle ABC's area is actually A times C divided by 2, right? And what about my little triangle here? My little triangle is actually C over 3 times A over 3 divided by 2, right? Then what about the trapezoid here? The trapezoid here, I think, is also very understandable. The C plus C over 3 times 2 divided by 2 because the height is 2. And A plus A over 3 times 2 divided by 2. B over 3, B, 2 plus 2. Is that right? This is kind of the 3 relationship, 3 areas for the 3 trapezoid. Adding them together, this is going to be here. Adding them together, this is going to be exactly equal to the big triangle's area, right? I think this is quite understandable. Okay, I'm going to do some quick analysis, do some quick simplification. You can find out all the way, you come to AC equals to 3C, 3B, 3A. That's it. Okay, I sort of finding the relationship, but I still cannot do too much because you see, I have like 1, 2, 3, 3 different factors here, 3 different variables in this equation. Even though I know ABC, there are integers, but still a little bit difficult for me to do, right? At least I have 2. Maybe I can do some factorization. But now I have 3. It's kind of like too drowsy to me, right? But don't forget, the question says what? There's another very important condition you didn't use yet. What? Right angle, right? ABC is right angled at B, aka PQR is also right angled at Q. So that being said means what? You still have another very important relationship, which is B square, oops, change the color. The Pythagorean theorem, right? Like I said, Pythagorean theorem is actually something so important and you have to use it from time to time. In our case, because B is here, B squared is equal to A squared plus C squared, right? This is actually something very intuitive. So that being said, maybe I can help to eliminate the B. B can be equals to underscore A squared plus C squared. I'm just going to plug in into here. At least I can get rid of some of the the variables, right? Dealing with 2 variables is by any means better compared with dealing with 3 variables. So if you put everything together, you're going to do some quick analysis. You can have something, I'm just going to put it here, 3C, 3 underscore A squared B squared. Okay, so do some quick analysis all the way. You can all the way come to here. AC minus 6C minus 6A plus 18 equals to 0. Just after some simplification, you get to all the way from here. This is actually another very important thing. As long as you see this, who can tell me what is the first conditional react? As long as you see this, what is the first conditional react? You can post your answer into the group chat, okay? This is our golden rule number 3. As long as you see such a form, what is your first conditional react? Yes, I see somebody has the answer right away. That's the famous Simon's favorite factoring trick, or for short, we use SFFT. That being said means what? As long as you see such a form, your first reaction is this form must be able to do some factorization. You must be able to factorize this form into something quite straightforward. Okay, you can actually do some Google search. Okay, this is like a boot camp. We don't really have time to expand too much. You can do some Google search to figure out how to do this SFFT. Okay, long story short, as long as you have this is a golden rule. You need to do a Simon's favorite factoring trick. You're gonna have this goes to A minus 6, C minus 6 goes to 18. This is extremely important, right? For AMC, they will test you every single year. For Euclid, it also tests you from time to time. So the question says A, B, C, they're all integers. So A minus 6, C minus 6 is also integers. And the two things, their product is equal to 18. So AKA A minus 6, C minus 6 must be a factor of 18. Is that right? So we just need to factorize 18 and then try to allocate all the factors to A minus 6, C minus 6. You get what you need. So how can I do this factorization? So A minus 6, C minus 6, they can be maybe 18, 1, right? Then what about 9, 2? These are two factors. 6, 3, right? Or maybe, I don't know, minus 3, minus 6, and minus 2, minus 9, minus 1, minus 18. You can actually do a little bit more, right? Minus 6, minus 3, so on and so forth. But that being said means what? You're going to do a lot of casework. That's going to be a lot of work, right? But bear in mind, think about it. A and C, the question is not asking you what is the value for A, what is the value for C, right? The question is basically ask you that all the possible size, as long as you give like a kind of like a bundle, you're good to go. So all the way come here, I'm gonna give you the golden trick number 4, golden rule number 4. As long as you're doing some factorization related discussions, as long as you don't really care A and C, which one is bigger, which one is smaller, what you're going to do is without the loss of generality, you can always let A is greater than C. Because A is greater than C, C is greater than A, it makes no difference. I understand this. It's going to generate different kinds of triangles, but the question is not asking you what is triangle, what is the A value for the triangle, what is the C value for triangle, right? As long as you give a triangle triple, it's good to go. So without a loss of generality, it can help you reduce your discussion, your casework significantly. So this is actually something very important as well. This is our golden rule number 4. So that being said, you can actually just take some higher, you can just basically take out as long as A is greater than C, and then you're good to go, right? So in that case, A can actually be 24, C can be 7, A can be 15, 8, 12, 9, 3, 4, 5, 0, minus 3, minus 12. This part, of course, you have to drop them, right? Because we're talking about the side lengths of the triangle, you won't be able to have any negative values. So that being said, these are actually all the possible values for A and for C. As long as you have A, you have C, using the Pythagorean theorem, you'll be able to determine the corresponding values for B. And that's it. That's actually how you're going to solve such a problem. A quick recap. This problem is also using what? Using the area ratio as the similarity ratio's perfect square, right? The question already give you two triangles. They are similar to each other. And then the question give you a quick hint. You see? Check it out from here. The area ratio is 9:1. It actually gives a very clear direction. You're going to use the similarities ratio, put a perfect square, goes to the area ratio, right? So with that information, it's very easy for you to list out the 3 sizes of this shape, and then taking from there, you will be able to determine, what's the relationship. And a very important golden rule I tell you guys, as long as you see something like here, don't forget you can use the Siemens field rate factorization trick. Try to factorize it into such a form, and then try to allocate a little bit, figure out all the factors for 18 from A to B, and taking from there, you get what you need. But the basic is still similarities ratio and make a perfect square is going to go to the area ratio. So this is actually our sample problem number 2. So far, so good? All right, if all good, let's go to the third sample problem. The third sample problem, I took a problem actually not from Euclid. I took a problem from Amy because it is using exactly the same strategy, well, with a little bit flowery. So hopefully can help you guys a little bit for this. All right, so this problem we're looking at is a problem that comes from 2015, Amy 1, question number 7. So the question says what? In the diagram below, ABCD is a square. Point A is the midpoint, okay, midpoint of the side AD. Point F and G, they lies on CE, AB, BC. As long as there's no specific condition, you can just fly them fairly quick. Such that FGHJ, okay, I have to FGHJ. This guy is what? This is actually a square, okay? This is a square, okay? And point K, point L lies on the JH and MN lies on AD and AB respectively, such that KLMN, this is also a square, okay? You're looking at two squares, okay? It looks like the only condition, a little bit tricky, is actually kind of the E is actually the midpoint. And other than E, everything is like, as long as you can create a square, you're good to go. With all those information, the question says KLMN. KL, like the tiny one, right? I'm gonna put it here. This one has area of 99. Then what is the area for the FGHJ, excuse me, FGHJ? Okay, you basically tell me a square's area is 99. You wanted me to determine another square's area. I think this is a very clear hint, right? Two squares, all the squares are similar to each other, right? All the equilateral triangles are all similar to each other. So kind of like you give me one area, determine another area, then automatically, as long as I can figure out the similarities ratio between these two squares, then I'm good to go. This is quite understandable, right? Okay, so the $1 million question is, how can I figure out the similarities ratio between these two squares? This is actually a $1 million question. And since this is Amy question, it's a little bit tricky, but you know what? Everything is also reasonable. You really understand where you come from. So let's check it out. Let's check it out. Before we jump to these two squares similar to each other, because the question doesn't give us something too flowery, like it doesn't give us too much information. The only information given by the question is what? E is actually the midpoint. Okay, so here I can actually do one conclusion. All the right triangles in my graph, they're actually similar to each other. Is that right? Any objections? All the right triangles in my little graph, they're all similar to each other. And let's say I'll take one. This guy is similar to this guy and similar to all the other things, so on and so forth. Right? I think this is quite understandable. Okay. And if go to one specific triangle, let's check it out. What is the relationship? If this is 1, this is also 1, right? Let's say I say AD equals to 2 because A is the midpoint. I just want to make my life a little bit easier. So 1 and 1. So this is going to be 2, right? Okay. So that being said, every single right triangle, you're going to have two short legs. They're going to have 1 to 2 relationship. This is not a 60 degree, right? 60 degree is the hypotenuse, but this is kind of 1-to-2 relationship. Okay, if that's the case, let's check it out. Is there something I can do some quick analysis? Let's check out this guy. Because you're dealing with these two squares, you want to figure out what is the similarity between these two squares. Then you want to get as close to the square as possible. I think this is quite understandable, right? So let's check it out. If I want to have a close look at these two triangles, this triangle and this triangle, they are also kind of similar to each other. Is it right? They're also kind of similar to each other. Okay, if that's the case, let's check it out from here. Okay, if I want to change the ratio a little bit, I'm not going to say something like this. Let's say if this is 1, if this is 2, let's say if this is 2, this is going to be 4, right? These are also, like I said, pretty much the same relationship, right? Okay, if this is 4, let's check it out from here. I do a quick m here. I do a height from h all the way to m. I can see these two triangles. These triangle and these triangle. Okay, like I said, first of all, they're all similar to each other. Second, they're actually one step more than similar. They're actually what? They're actually congruent to each other, right? These two triangles are actually congruent to each other. Okay, so that being said, if this is 4, this is going to be 4. And this is going to be 2, right? I change a different color. This is going to be 2. Okay. If this is going to be 2, this is going to be 1, right? Right? My MC is going to be equal to 1. My FM is going to be equal to 2. My JM is going to be equal to 4. Is that right? I think this is quite understandable, right? Nothing really special. But you know what? As long as you figure out this, you almost solve the problem. Why? Let's check it out. Your goal at the very beginning, we're trying to figure out some similarity between these two squares. And taking from there, I want to make a perfect square. I finish my job. But now I think I kind of get what I need. Let's check it out. My BC length actually equals to 7, right? My BC length actually equals to 7 because my HB equals to 4, aka my AH equals to 3, right? Okay, with this information, how can I figure out what is the similarities ratio between these two squares? This is the magic part. Let's check it out. I want to highlight 2 things. One is the blue one. The other one is the green one. Let's check it out from here. These 2 shapes, they're 2, let's say 2 diamond shape, right? Let's put it this way. They're 2 diamond shape. These 2 diamond shape are also actually similar to each other. Is it right? Because they're sharing all the same angles, and the other 2 are actually what? Right angle. So therefore, these 2 diamond shape are also similar to each other. Okay, let me try to write it out. So my diamond shape, AMLH, is actually similar to my diamond shape, BHGC, right? As long as these 2 guys, they're similar to each other, I should be able to figure out what is the similarity, right? So who can tell me what is the similarity? The similarity is actually AH over BC, right? That one is going to give you 3 over 7. AH, what is AH? AH is here. What is BC? BC is here. Okay? But as long as 2 shapes, they're similar to each other, not only one side is proportional, all the sizes are proportional, right? All the sizes are actually proportional to each other. So that being said, as long as AH over BC is actually 3 over 7, then what about A, let's say, what about ML? Over HG. Is it right? ML is here. HG is here. They should actually fall into the same proportional relationship, right? As long as two diamond shapes are similar to each other, AH over BC will be equal to ML over HG. But what about ML and HG? ML and HG, they're exactly the side of my small square and the side of my big square. Is it right? So that being said, okay, if the question asks me ML over HG, if I make this guy a perfect square, this is going to be my little squares area over my big squares area. Is it right? I think this is something quite understandable. So we are actually using the diamond shape as a middleman. From the diamond shape, I figure out the relationship between ML over MG. And ML over MG happen to be the two sides of my small square and my big square. Is that right? So that being said, it actually means what? So my small one over my big one is going to be 3 perfect square over 7 square, right? And this is 99, right? So the big square is going to have an area 593. So this is actually a thinking process. Again, always use the thinking process. See, this problem, like the only solution is one-liner, right? Using this one-liner, and then you're good to go. But the thinking process, what is the thinking process? Try to understand from the areas of similarity ratio, you find out, okay, I need to determine the side similarity ratio. And how to determine the side similarity ratio? We're actually with the help of this two diamond shape. Because this two diamond shape, they're similar to each other, I figure out the similarities ratio. So therefore, ML over HG is going to be exactly the same thing. Okay, so far, so good? All right. So this is actually the third problem I gave you guys as a sample, how to use the similarities relationship, go to the areas relationship and solve the problem. I think 3 problems is good enough, and hopefully you guys understand the sense how to do all such problems. If all good, let's continue. Okay, just now I just mentioned like area problem is very important, right? And we just finished the first part. Similarities, perfect square goes to the area ratio, right? There's another very important thing talking about area, which will be tested from time to time, is actually the area compensation method. What is that? Sometimes if you directly determine the area, it might not be so straightforward. You need to do a little bit of workaround to add something, to subtract something, so on and so forth. Try to compensate the area. And taking from there, you might be able to solve the problem. This is actually a very important trick for the Euclid problem as well. You know what? Let's go for a real problem and try to analyze how you can solve problems using such a strategy. So this is actually our second category, the compensation. So as a sample, again, we're looking at a problem that comes from Euclid. It is a problem that comes from 2012. Euclid, question number 9b. Like I said, our lecture focuses on from number 8 all the way to number 10. Like the easy peasy problem, you do it by yourself, right? Our bootcamp is trying to use some relatively difficult problem and give you guys some big direction how to solve and how to think for the big problems. So let's check it out. So this problem says what? In the diagram, you have the quadrilateral ABCD and has the points MN on AB and DC respectively with such a weird condition. AM over AB, let's try to highlight it. AM, over AB equals to NC over DC, okay? It's kind of like the two things on the top and on the bottom, okay? Line segment AN, DM, they intersect at P, while BN, CM, they intersect at Q. Okay, prove that. The area of the quadrilateral PMQN, let's check it out. PMQN is here, right? The red one. The red one is equal to the sum of the area APD. APD is here. The little triangle, the little green one on the left, and the BQC, let's change a different color. BQC is the blue one on the right. Okay, this is what I want to prove. Okay, this is like super nasty, right? The PMQN is something like a tooth, like kind of like deformed, like a quadrilateral in the middle, right? And then APD and the BQC, there's something one on the left, on the right. This is totally undoable, right? It is impossible for you to do this because they don't really talk to each other and they're totally like a weird shape. There's no way for you to do. As long as you see such a problem, you must have a very clear direction. As long as three things are floating there without any connection, so on and so forth, there's no way for you to determine the area as is. You need to somehow finding some trick in order to kind of like do maybe find out a relationship. Listen this, right? You need to find out a relationship between this green one, the red one, the blue one, and taking from there, you can solve what you need. But how can you find out the relationship? This is actually a very common strategy, is using the compensation method. What is the compensation method? Is maybe you need to add something to the, or kind of like three triangles. Maybe subtract something from your three different triangles. And hopefully after you add something, after you subtract something, you can find out some relationship. And taking from there, you figure out what you need. So this is kind of like too vague, right? So let's try to write it on a paper and then you understand where it comes from. So what you need to do is, so want to show, right? So the area of PMQN is equal to the area APD plus the area PQC. But like I said, they are totally not touching each other. Is there a way for me to let them touching each other? Is there kind of things I can do with some compensation? The answer is correct. Why don't you check something here? I'll use the color maybe black, okay? There are something here. There's a big triangle here, which is left into black. There's this also another triangle here. As long as I can maybe add on these two triangles, maybe at least I'm looking at like a real triangles, right? Not like a triangles floating there, not a triangles floating there. So that being said, maybe this is kind of like a compensation. I just need to prove maybe as PQM, I add this triangle, what? PDN. Add this triangle QNC. If I can prove exactly the same thing, add the triangle PDN, add the triangle QNC. You see, I'm actually adding two things. This is kind of a compensation, right? Compensation. I add two parts on the two sides of this equation. Of course, I didn't change anything, right? They're exactly the same. However, as long as I put this compensation, check it out. My PMQ, my red one, plus this two black one it goes to the area of triangle MDC, right? Okay. My green one plus the big black one goes to triangle ADN, right? And my blue one plus the little black one goes to the triangle BNC, right? Okay, now what I have to do is I just have to figure out MDC. Okay, now MDC, let me try to use the color to highlight it. MDC is here. My red triangle is equal to the area of ADN. My blue triangle, and also B and C, my maybe change the color, my green triangle, right? And my work is done. This, at least I make my life a little bit easier. I'm actually dealing with some triangles. They have the side on the DC, something a little bit more shaped rather than otherwise. Okay, so let's get started. How are we going to determine the area of the three triangles? Let's check it out. To make my life easier, I'm going to let DC equals to X. Okay, and because you have an N in the middle, maybe I'm going to let this is the TX. This is 1 minus TX, okay? It doesn't matter, just want to make my life easier. And also, if you're dealing with the triangle's area, you need to have the height, right? Height, height, height. So maybe this is A, this is M, this is B. Nothing really special, right? I just have to plug in the value. So what is the triangle MDC's area? That one is easy, right? MDC is 1 over 2 x times m, right? 1 over 2 x times m. Then what about my triangle ADN? My triangle ADN is here. This is A, this is TX. So that one is going to be 1 over 2 TX times A. Then what about my triangle BNC? My BNC, this is B as the height and 1 minus TX as the bottom. 1 over 2 TX B, right? So do some quick simplification. You just have to show, we just want to show m equals to t times a plus 1 minus t times b. As long as I can figure out this, my work is done. Okay? M equals to t times a, 1 minus t times b. Okay, what is that? So in order to make my life easier, I'm just gonna do a screenshot. I'm gonna cut this and then we'll drag it into the second page, okay? Because we really need this save photo, okay? Let's go to the second page. We'll see what we can do using what we just got. I just need to prove m equals to t times a and 1 minus t times b. What can I do about this? Let's check it out. It looks like most of the work focuses on such a shape. I'm gonna highlight it here. This is my shape, right? This is a trapezoid, right? I'm gonna drag it out, okay? To make my life easier, I'm just gonna drag it out. A, B, maybe I'm gonna give a name, EF. This is E, this is F, this is M, right? This is N, okay? So now I know this is A, this is B, this is M, right? Okay, I wanna find a relationship. Okay, M equals to TA plus 1 minus T equals to B, times B. What you can do in such a thing? You're dealing with a trapezoid, right? As long as you're dealing with a trapezoid, I think you guys should remember a very common auxiliary line is actually do something from here, right? You cut this trapezoid into a rectangle and also a square and also a triangle, which is exactly the same thing when I talk about from day one, right? When you're dealing with kind of a polygon problem, try to convert it into what? Into triangle problems, right? Triangle is something what you're familiar with. So if that's the thing, let's check it out. If I call this guy with R, right? Obviously, triangle AMR is actually similar to triangle maybe AS, right? ABS. Okay? AMR is the little triangle, ABS is the big triangle. If that's the case, you're going to have what? MR over BS will be equals to AM over AB, right? This is easy peasy lemon squeezy problem, right? Everyone knows that. Two triangles that are similar to corresponding size, they are proportional to each other. Okay, but you are trying to have something like AB, something like the TM, right? That's where we come from. Then try to convert it. What is MR? MR is actually equals to what? M minus A, right? MR is M minus A. A is here, right? Then what is BS? BS actually B minus A, right? B minus A. Then what about AM over AB? AM over AB, I don't really know because the question didn't give me too much information, but don't forget, there's another very important information you didn't use yet. AM over AB equals to NC over DC, right? So this guy equals to NC over DC. What is NC over DC? Let's check it out. Let's check it out. NC over DC. NC over DC. That is actually 1 over T, right? Your NC is 1 minus T, X, and your DC is entire X. So NC over DC is going to be 1 over T. Trust me, this is like so easy. As long as, see, I'm going to use different color. As long as you do some rearrangement for this guy, M minus N over B over A, M minus A over B over A equals to 1 over T, you would directly have M equals to TA plus 1 over T B. That's it. QED. You see? Fairly understandable. Okay? Fairly understandable. This is actually a famous way, what we call a compensation method. So let's do a quick recap. Okay, what we have learned in such a problem. In this problem, the question gives you a bunch of areas, but these areas are actually floating there in the middle of nowhere. There's no way for you to solve the problem as this. You must kind of find a relationship, do some tricks to find out a relationship between all those kind of shapes, and taking from there, you will be able to solve the problem. How to find out a relationship? Pretty much using the compensation method we talk about. For this problem, we're adding something. Trust me, for some problems, you have to subtract something, but the strategies are exactly the same. After you're adding something, after subtracting something, you are trying to find out a relationship. And so therefore, after those, they can really handshake together. They can talk to each other, and then you can use whatever you learned so far to solve the problem. Number one. Number two is, like I said from day one, as long as you're dealing with any trapezoid and quadrilateral, try to convert it into a triangle problems, because triangle is a lot more straightforward for you to solve the problem rather than using the trapezoid, using this complicated quadrilaterals. This is the golden rule, which never change for the entire AMC or the Euclid. All right? I think the compensation method is not very, very often, very, very common. I think one example is good enough. Okay, so let's continue. The area, the first one, we talk about the similarity thing, right? The second one, we talk about compensation. Actually, this is also a very important method. Always dealing with this area, this kind of things. We call it rotation and reflection method. This is actually very explicitly for Euclid and the COMC. AMC barely tested, I have to say this. I also do AMC, it never tested. It's only the Euclid and the COMC likes to test it. So let me give you one example each, then you will understand where this problem comes from. Rotation and reflection. The first one, let's do a rotation problem. I'll give an example that comes from the COMC, and it's exactly the same thing for the Euclid. Let's do this, number two. So this problem says something like this. You have a trapezoid ABCD has AD parallel to BC. I'm just gonna write something here. You have a trapezoid and something like here. Okay. This is A, D, B, C, right? You have AD parallel to BC, and B angle is 90 degrees. AB is equal to BC is double of the AD. I think my graph is quite proportional. P is a point inside the trapezoid ABCD. Okay, P is a random point here. You have, oops, sorry. Jump it back. Okay, you have P here, something like this. P, you have PA equals to 1, PB equals to 2, P3 equals to 3. Okay, with all those information, the question is asking you to determine what is the area of the trapezoid ABCD. Okay, this is actually another very important thing I want to talk about. Conditional Okay, can you mute yourself? Please try to make sure you mute yourself. Okay, in order to make sure the quality of our lectures, because today is an open course, we have a lot of students. Please try to mute yourself. Okay. So this is actually our golden rule number 5. As long as in the future you're looking at a problem like this, the question gives you a weird shape. It can be triangle, can be trapezoid, can be whatever. And then they give you a point in the middle, kind of using the point, making some connections. I don't know what kind of connections, right? Different kinds of connections. Okay. And from the connection, the question weirdly give you some number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever. And then taking from there, the question asks you something. Trust me, as long as you see such a shape, especially in our Euclid, most likely you're going to either use rotation or using reflection. This is like pretty much an experience, okay? Because every single number by the exam, they're not given for fun. There must be some underlying reasons behind that, okay? And you need to take advantage of this reasoning behind this 1, 2, 3, 4, 5, 6, so on and so forth. You'll be able to do some magic taking from there, okay? Big direction is, as long as you see the weird shape, have a weird point, 3 sizes, 4 sizes, I don't really care, give you some segments, and then asking something. Most likely, these 1, 2, 3, 4, 5, 6, they're not given for fun. There will be some very beautiful coincidence you're going to see in the future. I'm going to show you in a bit. And then try to use this to try to use the rotation and reflection as one of the big strategy. So the other question you might ask me there, hey, Alex, what is reflection? What is rotation? This is the big direction how to do it. As long as you see such a thing, you are trying to construct congruent triangles. You are trying to construct congruent triangles. And taking from there, you'll be able to transfer some kind of relationship from one side to the other. You'll be able to transfer the relationship from one side to the other. How to do that? I'll show you an example. In this problem, you see, the relationship I have AB is equal to BC is equal to twice of the AD, whatever, right? So what I'm going to do is I'm going to rotate my triangle ABP, rotate from the B point. I rotate to here. I'm going to use. So my P goes to P prime. I do a rotation, okay? I do a rotation. So as long as I do a rotation, of course, triangle ABP is congruent to triangle ABPC CBP prime. Is it right? Because AB is the same as BC. It is quite possible I find a P prime point lower down BC. I can make sure CBP is congruent to ABP, right? CBP P prime is congruent to ABP. Okay, if that's the case, let's check it out. These two angles will be the same, right? ABP will be the same as CBP prime. Okay, because previously the question says ABC is a 90-degree angle, right? It's a right angle. Now, when you do this transfer, when you do this rotation, you can actually figure out my PBC, my PBP prime is also 90 degrees. Is that right? Because these two black dots, they are the same. The black dots plus here equals to 90 degrees. Of course, this is also 90 degrees. Right? I think this is quite understandable. This is quite understandable. Okay. One more thing. Because these two triangles are congruent to each other, you can get what? BP is the same as BP prime. BP prime. So that being, if I use different color, this guy is the same as this guy, right? Of course, they're congruent to each other, right? These two sides are the same. Okay, now you're looking at what? You're looking at BP P prime. This is a right triangle, and also you have two sides are the same. So AKA, if I do a connection, this is going to be 45 degrees, right? This is also going to be 45 degrees. Is it right? This is quite understandable, right? So I say angle, let me say this is A, this is B. Angle A is equal to angle B is equal to 45 degrees. Okay, let's check it out. Previously, you told me this guy is equal to 2, right? BP is equal to 2. So this guy also equals to 2. And then using this as our right isosceles triangle, PP prime is going to be 2 under root 2, right? This is quite understandable. And then you tell me the red triangle is actually congruent to this green triangle, right? Let me try to highlight it here. The red one is congruent to the green one. So therefore, if PA is equal to 1, CP prime is also equal to 1. This is quite an understandable thing, right? Nothing really special. So that being said, it means what? Okay, I have already found out the 3 sizes of this triangle. I'm gonna highlight it here, right? This is the blue triangle. The 3 sizes of this blue triangle. Is it right? Okay, do you find something special? I find the 3 sizes of this blue triangle. Did you find something special? One is 3, the other one is 2 under root 2, and the other one is 1. This is what? This is a right triangle, right? This is a right triangle. Okay, if this is a right triangle, this is so beautiful. Okay, this is going to be 90 degrees. What a coincidence, right? Why this going to be a right triangle, right? Trust me, do you still remember? Like I said previously, all those numbers given, they're not given for fun. Especially for this rotation and reflection problem. The number will be given in such a beautiful fashion that during your calculation process, you're going to find out either a right triangle or isosceles triangle or kind of other triangles. But nevertheless, this is going to be something very special. Okay, as long as this is a right triangle, I think your life can be so easy. Check it out. This guy is going to be what? 135 degrees, right? 45 plus 90, 135 degrees. And if I drag out this triangle, let me try to highlight it. if I drag out this triangle, I'm going to put it here. This is B, this is P, this is C, 135, right? This is 2, this is 1. Using the cosine law, you will be able to determine the value for BC. Is that right? As long as you determine the value for BC, the question says what? AB is equal to BC is equal to AD. So this value you know, this value you know, this value you know. So easy, you will be able to determine the area of this trapezoid. Is that right? So far, so good? So this is the beauty of the rotation. So you can actually construct some congruent triangles. So therefore, you'll be able to transfer. When I say transfer, you see, this PA comes to here, right? PA at the very beginning is here. Now it's come to here. At the very beginning, and PB is here. Now it's come to here. You'll be able to transfer some relationship from one side to the other. Therefore, you'll be able to construct some kind of right triangle, isosceles triangle, equilateral triangle, and taking from there, you'll be able to solve the problem. This is actually something very, very important. Okay? This is how we're going to do for the rotation. Let's give you another problem talking about the reflection. And then you will totally understand. Within these two things together, side by side, you will have a better understanding why this rotation, why this reflection are so important. So let's check it out. The second problem. The second problem is actually a Euclid camp problem. It's a mock Euclid problem. I'm going to give you, this one is using the reflection. Let's check it out from here. The question says, you have a triangle ABC, and this triangle ABC is actually something like here. I'm just going to put it maybe here, 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 something like this. And again, you have a point in the middle, here, here, here. Exactly the same thing what we introduced. Let's check it out for this problem. You have a triangle ABC, A, B, C. You have a BAC equals to 60 degrees. This is 60 degrees. AB is twice of AC. Point P is inside the triangle ABC. PA equals to under root 3. PB equals to 5. PC is equal to 2. With all those information, the question asks you to determine what is the area of this triangle ABC, which is quite similar according to our pattern, right? You have a weird shape. This is like a triangle, and you have like a point in the middle. They give you some kind of like 3 distance, so on and so forth, and then ask you to determine what is the area of this triangle ABC. Okay, so this problem, we're going to use reflection rather than rotation. So what is the reflection? The reflection, I think the name really speaks for itself. I'm going to reflect my P point based on AB, AC, and BC. So let's check it out. I'm going to find a P prime here. Maybe I'm just going to put it because I'm going to have 3, so I'm just going to call P1. P1 is actually a symmetric point versus AB of my P point. This is going to be, I don't know, P2. P2 is going to be a symmetric point for AC. And the P3 is going to be my symmetric point for BC. And then I'm going to make a bunch of connection. Connect here, 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 here. I know it's a little bit crazy, but you understand where I come from as long as I finish everything. Let's check it out. Let's check it out. At the very beginning, the question says, angle BAC is 60 degrees, AB is twice of AC. Then I think this is quite understandable. Triangle ABC is actually a right triangle, right? This is actually our 90 degrees. Okay, and this is going to be 60. This is going to be what? This is going to be like 60 degrees, right? BAC. This is going to be 60 degrees. This is quite understandable. Okay, let's check it out from here. as long as I do a reflection. Let's check out this part. Because I did a reflection, I can see that my triangle APB is congruent APB, right? I have P1B is equal to PB. This guy equals to this guy. If I use different color to highlight it, I think it's easier for us to know. P1B is same as P2B. And same thing, don't forget, my triangle P2CB is also congruent to triangle P3CB, right? So that being said, my BP2 is going to be the same as my BP3. This is quite understandable, right? Nothing really special. So that being said means what? P2B is equal to P3B. P1B is equal to PB. P2B is equal to, P1B is equal to PB, yes. And my PB is equal to P3B. These two things together is actually going to have what? P1B is going to be same as P3B, right? P1B is the same as P3B. What is that? You have a isosceles triangle, right? My triangle P1, B, P3, this is going to be an isosceles triangle. Let me use the color to highlight it. Use all the blue color. Oops, I'm going to use all the blue color. So this is going to be an isosceles triangle. Okay, actually, this is going to be more than an isosceles triangle. Let's check it out from here. At the very beginning, this is going to be what? This is going to be 30 degrees, right? Now you kind of double this two angle because this part equals to this part. This part equals to this part. The cross plus the dot equals to 30 degrees. But this guy is going to be what? Angle P1, BP3 is going to be equal to 60 degrees. Is it right? Using your reflection, you're going to have 60 degrees. So that being said means what? Your triangle P1, BP3 is going to be an equilateral triangle. More than isosceles, equilateral triangle. So that being said, it means what? If you have 5 here at the very beginning, now 5 come to here, 5 come to here, 5 come to here. Is that right? So far, so good. I successfully finished my transfer, right? I transferred from the middle PB pretty much into P1B, P3B, and P1, P3. Okay, same thing. Let's check out here. Let's check out here. I'm going to do a connection between P1 and P2. Between P1 and P2. Let's check it out, okay? After I did a reflection, I can basically figure out, okay, let's check it out from here. This angle now becomes 120 degrees, is it right? This angle actually becomes 120 degrees. Is it right? Okay, if that's the case, check it out. This guy is what? Under root 3. Because I did a reflection, this guy also goes to under root 3. I did another reflection, this guy also goes to under root 3. So with all those information, P1, P2 can actually be what? Who can tell me the value for P1, P2? Let me highlight it. P1, P2 is going to be something like this. 120 degrees under root 3, under root 3, this is going to be 3, right? So this one is going to be 3. This one is going to be 3. Okay. The last one, we go to P2, C, P3. At this moment, I don't really know P2, 3, PC, P2, C, P3, they're collinear or not, right? Because P2 was actually constructed using the reflection of P as the AC, right? And P3 is actually using the reflection of P using BC. I basically know, okay, there are 3 points here. 1, 2, 3. However, can I use exactly the same strategy to find out P2, C, P3, they're collinear or not? Think about it. Can I think about using the same strategy I did before to figure out maybe P2, C, P3, they're collinear or not? Actually, the answer is very conspicuous. They are collinear. Why? Check it out. At the very beginning, this is what? Let me change a different color. At the very beginning, this is what? 90 degrees. Now you tell me this guy equals to this guy equals to this guy. Because the cross plus the dot equals to 90. So 2 dots plus 2 cross, there will be 180 degrees. Is it right? So that being said, P2, C, P3, they're actually collinear. Is it right? Collinear. So that being said, okay, P2, C, P3, you can actually calculate the lengths. They're actually within the same lengths, right? That they're within like the same line. And how to do that? Exactly the same thing. At the very beginning, your question tell me this is actually 2, right? PC is equal to 2. So this is going to be 2. This is going to be 2. So this guy is going to be what? It's going to be 4, right? The P2, P3 is going to be 4. Voila. In that case, let's check it out. You are actually, again, goes to a perfect coincidence. P1, P2, this is 3. Change a different color, maybe to blue. P1, P3, it goes to 5. And your P2, P3 is equal to 3. It's equal to 4, excuse me. So that being said, this is what? This is going to be a 90-degree triangle, right? Do you still remember what I mentioned? As long as you're dealing with the reflection or rotation, trust me, 99% of, not 100%, let's say this way, 100% of the time, you must see some beautiful coincidence during the calculation process. Either a right triangle, equilateral triangle, a square, so on and so forth. Because every single number is actually given for a reason. All those kind of reasoning is actually speaks for itself after all the numbers are calculated, right? So if I highlight it from here, let me change the color. It goes to here, my black one. My black one. It is very easy for me to determine the black area, right? It's a right triangle, all right, no, the 3, 4, 5. Okay. Then the last one is, what about the red one? The red one is here. The red one is the obtuse right, the obtuse isosceles triangle, which I highlighted from here. Okay, let's check it out. The question asked me to determine the area of the triangle ABC, right? This is where I come from, right? The question asked me to determine the area of triangle ABC. Of course, I cannot directly determine it because I don't know the shore, like 2 legs. However, after I do such a reflection, I actually check it out from here. In my current graph, my total graph contains 3 parts. I have a blue triangle, which is what is that? Which is an equilateral triangle. an equilateral triangle with a side length 5. At the very beginning of the lecture, we talked, you guys, right? 4, let me change the color. 4 as the denominator and the root 3 as the numerator, a square, right? That's going to give you the area of the blue equilateral triangle. The black triangle is what? It's a right triangle. Of course, you can calculate what is the area. And the red triangle, it's a isosceles triangle with the top angle equals to 120 degrees. Of course, you can also determine the area. So my triangle ABC's area is actually 1/2 of the sum of the 3 triangles. Is it right? So my triangle ABC's area is actually 1/2 of triangle P1, BP3, triangle P1, P2, P3, triangle AP1, P2. Is that right? Because they're all reflection. I reflected 3 times. They're all congruent. And then this is only 1/2 of the original triangle. Is that right? So that being said, you figure out this value divided by 2, that's going to be our triangle ABC's area. Okay, so far, so good? So actually, in today's homework, I'm going to give you a problem from 2016 Euclid number 9B question. This is exactly the same thing using rotation and reflection, what we introduced in today's lecture. So I'm going to give you a sample question, and then you figure out the Euclid question by yourself. Okay? So a long story short is this is the way how to determine the area. Okay? So as a quick wrap up, in today's lecture, we focus on the first chapter of our bootcamp, aka the 2D geometry. We're focused on the triangle and the quadrilateral, polygon, so on and so forth. You know what? A big analysis, like an analysis indicates for this 2D geometry, the area method is like so important. It takes the majority of the problems, and also much like the area method, we can say kind of like a foundation for all those kind of like the 2D geometry related problems in Euclid. So that's the reason we actually break our today's lecture into 3 major categories. Pretty much all of them focus on the area method. A quick recap, the first category, we actually introduced the similarity, right? As long as you have similar triangles, you make a, what should I say, the similarity, and then you got a perfect square of the similarity, you'll be able to determine the area ratio. And then the second method we actually introduced is actually we call it the compensation method. As long as you have some angles, some triangles, some quadrilaterals, whatever, they're flying all over the places. They do not talk to each other. There's no handshake for those triangles. There's no relationship for the shapes. There's no way for you to solve. You need to basically find out or construct out the relationship. How can you construct out a relationship? Adding something, subtracting something. Okay? And the third method, what we introduced, is pretty much something explicitly for AMs, for Euclid and COMC, is using the rotation and reflection. As long as you give the weird shape, a weird point in the middle, try to do some connections here and there, trust me, you're pretty much going to do the reflection or rotation. And one more thing is all the numbers are given for a reason. And everything, when you construct everything, you're going to very happily, very coincidentally find out there will be a right triangle, there will be a equilateral triangle, there will be a isosceles triangle, so on and so forth. You see, in our problem, we have them both. We have the right triangle. Let me change the color from here. You have the right triangle, you have the equilateral, you have the isosceles. So everything they're connected. So therefore, that being said, and this is like the big direction how to solve the problem. All right. And yeah, I think that's pretty much for today's lecture. The first lecture will focus on the 2D geometry. From the next lecture, we're going to go to the 3D geometry and the coordinate geometry. All right. And I thank you guys for your time. being with us. It's almost like 2 hours. And hopefully you guys learned something for today's lecture. And this is going to be helpful for our upcoming Euclid exam. If you're interested in the lecture, you can ask your parents to contact me and register for the lecture. All right. Thank you, guys. I wish you guys a nice weekend. Bye, guys.